This video is meant to be viewed after having read and reviewed modules 1, 2, and 3. This video is meant to explain the concept of axis in an eyeglass or contact lens prescription using a three-dimensional model. If you've read through and reviewed modules 1, 2, and 3, you will have seen this concept explained as a flat representation or on paper in the examples of flat transposition and the optical cross. We hope to make this idea a little bit clearer using our three-dimensional model, which we're going to look at now. This is our 3D model of the human eye, and on the outside of the globe or the orbit, we can see the ocular motor muscles which control the movement of the eye. Those control left, right, up, down, in, and out, and allows the eye to look around. On the back of the eye, this piece represents the optic nerve. The optic nerve is the nerve that sends the light impulses that come into the eye up to the brain for interpretation to see. Always remember that we see with our brain, not with our eyes. Okay. We're not going to go inside the three-dimensional model of the eye. And the first piece that we're going to look at is this, which represents the vitreous humor of the eye. The vitreous humor is a clear, jelly-like substance that gives the eye support. Working from the outside in, the next piece would be the cornea, which we're going to come back to in just a moment. Behind the cornea is the iris and the pupil, which regulates the amount of light that enters the eye. Behind that, situated about here, is the crystalline lens. The crystalline lens is a biconvex lens, a magnifying lens, that changes shape so that we can see things up close. As something gets closer to the eye, this actually changes shape and becomes more convex or more plus in shape, magnifying the object so that we can see it. The crystalline lens is involved in presbyopia and cataracts, which are covered elsewhere on the site. And now we're going to get back to our cornea, which is represented by this piece. And remember that a perfect cornea in the perfect eye, or the emmetropic eye, is consistent in shape across its entire surface. It's a perfect sphere and would measure the same in all directions. Remember that all light passing through a perfectly spherical cornea will gather at one single point behind the lens. If we think about light passing through this cornea and into this eye, it would pass through the iris and the pupil, through the crystalline lens, through the vitreous humor, and it would strike an area on the retina back here called the macula. It's just off the head of the optic nerve. The macula is the area of the retina that contains a high concentration of the rods and cones, which are the light-sensitive nerves that see light and send the images to our brain for interpretation. Remember that a spherical cornea is shaped like the top of this tennis ball. It measures the same in all meridians, in all directions, and has a consistent shape. Now, what happens if our cornea is shaped more like this football? We can see that it has two different curves, a long curve or radius and a short curve or radius in this direction. Notice that the longer curve is less steep than the shorter curve or radius. The shorter the radius, the steeper the curve. The steeper the curve, the higher the power. The higher the power, the more it will bend the light. If we think of this football as a cornea with two different curves, or what we call astigmatism, then the lens that we use to correct their vision will also have two different curves just like this football. So if the light passing through the lens is going to fall at two different points, we need a way to tell the lab where to place the curves. This is done by using the notation of axis. In Module 2, I used an example of -6, -3 to work the flat transposition and optical cross examples. This means that I have a lens with a total power of -6 in one meridian and -9 in the other meridian 90 degrees away. If we look at this lens, you can actually see the two different curves. I have a thin edge here and here, and I have a thick edge here and here, 90 degrees apart, which is indicated by my square. My thin edge is my -6 curve. My thick edge is my -9 curve. You can see that the 9 curve is the steeper curve, so it is more powerful than the -6. This lens will never be more than -9 or less than -6. Any point on the lens between those 2 points is either building minus power to -9 from -6, or becoming less minus or more plus from -9 to -6, which is where plus or minus cylinder form comes from. Let us assume that you went to the eye doctor and she finds that for you to see clearly you need -6 power at 45 degrees and -9 at 135 degrees. She would write the prescription -6, -3, axis 45 for you. The number 45 is the axis and tells you or the lab where to place the -6 power. I can now see this and actually align my lens by rotating it to place the -6 at 45 degrees in front of my patient's eye. 90 degrees away will be -9 at 135 degrees. You are doing the same thing when you spot or dot up a lens in the lensometer or dispense a contact lens with an axis. This concludes our video presentation on the concept of axis using a three-dimensional model. For more instructional videos, join us at opticianworks.com. Thank you.